So let's get on to something that really got me interested in chemistry, actually, and that's chemical reactions, that changing, that taking a reactant and changing it to a product, that converting, imagine you eat a Big Mac, right? Converting those Big Mac burger patties, buns, sesame seeds into hair and kidneys and livers and whatever else, eyeballs and whatnot. So this changing matter, right, is a big part of chemistry. And chemical reactions is this process where we change reactants into products. So changing matter, right? Otherwise, everything would be unchanging and boring. So how do we change things? I mean, we're just a big chemical reactor ourselves. We eat, we drink, we breathe, and through the course of our life, we change. Sometimes we're good, sometimes we're bad. So we have chemical reactions. We have chemical equations. So we describe what we call a word equation. I'll just write EQ, short for equation. And if, say, we had an iron nail or something that we left outside, we know it would rust, and so we could write a word equation for that. We could say the iron and is reacting with oxygen from the air. So we're using words here, and we're using a plus to indicate that the one thing is combining with the other. We write an arrow to represent the change. Sometimes we refer to this as the yields symbol, I suppose. It's just an arrow. The thing on the left, the iron and the oxygen, is what we start with. And I've already used this word. I think these are the reactants, so the things we start with. And the yields indicates a change. And then the product, this hydrated iron 3 oxide, or we can just call it rust for short. And so the rust, okay, the final thing we've changed it into, these are the products of the reaction. And if you buy those cheap dollar hand warmers, maybe they were like $1 for 2, and they're just a little pouch encased in plastic, and you tear the pouch open. It's like a tea bag inside, although not Earl Grey, I'm afraid. And as soon as you open it up, right, it starts to get warm, and within a minute or two, it's nice, keeps your hands nice and toasty. And what you have inside of there is essentially iron filings, and the plastic keeps the oxygen out. And as soon as you tear open the plastic, oxygen from the air comes and meets the iron filings. There's a lot of surface area, so the oxygen can easily react with it and converts it into rust. And, okay, so what else is going on here? We're not really interested in the rust, but it also forms heat. We'll talk later. This is an exothermic reaction, a reaction that gives off heat. We'll talk about why, but mostly with a hand warmer. We're not interested in making rust, although rust is actually pretty easy to make, it turns out. But we're interested in making heat, so that's a classic example of a reaction that's used to make heat. Now, it's okay to say words, I suppose, but the word equations are considered a little clumsy, and so we normally write what's called a chemical equation, so EQ for equation, because I'm lazy, and instead of iron, we write Fe. Instead of oxygen, we're going to write O. We'll see later on that the oxygen atoms come as pairs, so just like ladies go into the bathroom, they go in a pair, oxygen atoms go in a pair, and oxygen is a gas, and iron is a solid, so we'll write a little S after it. We'll see that in order to keep the same number of atoms on one side equal to the same on the other, we're going to have to put numbers in front, and this is telling us that 4 iron atoms are going to go in on one side and are going to move around and change into rust on the other side. So there's our yield arrow, and we're going to write Fe2O3, and a little S after, and a 2, and still early days. There's a whole section on chemical equations, chemical reactions, so don't worry too much about it. But essentially, the 4 iron atoms are being incorporated into rust, and we've got 6 oxygen atoms that are going to get incorporated here. And so you can see, right, that this just looks very different from this. So this is our chemical equation. So elements, we said earlier, are sort of like the building block of the universe. They're those things that you can't break down into anything simpler. And there are 118 known elements. So as far as we know, everything in this universe, whether it's a compound or a mixture, we can break it down into 118 different things. So at most, if we took your body and we poured a bunch of acid over you and burnt you and did whatever it was, we could make at most 118 different piles of these chemical elements that we could not break down and make into anything simpler. And you probably know a lot of these, so take a moment and think of a few. I think I asked you earlier. We've talked about some earlier, actually. So, for instance, hydrogen is an element. Oxygen, the thing that we are breathing in, is an element. Carbon, so we are carbon-based life forms. Most of those complicated molecules in your body have carbon atoms in sort of ring structures inside of you. And so those are 3 of the 118 elements. And, well, say in hydrogen, right, takes a little bit of effort, right? Hydrogen, right? It's a little bit long. We got the spelling. We normally have a shorthand. So we normally use 1 or 2 letters as a symbol. And so we normally use a symbol for these things because it's a lot easier drawing a symbol like a stick figure for a person instead of having to take a picture of someone, right? So we have a very quick, easy way to refer to something. 1 or 2 letters. The first letter is always capitalized. And the second letter, if it's present, is always lowercase. So, for instance, hydrogen is the most common atom in the universe, actually. It's the most common element in the universe. Like 99% of all atoms in the universe by number are hydrogen, let's say. And we just use the symbol H. So just a single capital H, and that is hydrogen. But if we go to helium, which is the second most common element, that's a tongue twister. Helium, right? We can't just say H because then we'd get them confused, right? We mean hydrogen or helium, right? We can't have the same symbol for 2 different things. So we use a second letter here, and we're going to use a lowercase e. And so we write HE like that. We don't ever capitalize. If you are one of these sort of mad texter people who types everything in uppercase letters, right? Because it looks more professional maybe, or you're just mad. Your element names must always have the second letter lowercase. So if I saw HE with the big E, I would say, oh, I have no idea what that is. You haven't paid any attention. But if we take something like carbon, very, very common element. And a lot of the very common ones or the important ones just are given a single letter. Whereas we had something like calcium. Calcium, right, is we can't just use C, so it's Ca, and so on. And some of them are pretty easy, right? You might just think, oh, it's just the first letter, or the first letter and the second letter, and that's not too bad. And a lot of them are that way, but some of them are definitely not. So, for instance, sodium, the thing that gives street lamps their orange color at night. If you've ever been out in the city in the evening and you've seen that orange color everywhere, they've got little chunks of sodium that they pass electricity through and heat up, and the vapor gives off that beautiful orange color, and its element symbol is actually Na. And if you look at Na and you look at sodium and you think, well, there's no N in there and there's no A in there, so what are they smoking, those chemists? Why did they use Na? And that's because the old Latin name for sodium was natrium. And you can see Na, right? So that's the Latin name for the element. And so unfortunately, you do have to learn some of these. And there is a table in your textbook, and it is table 1.2. And if you look at your ebook, you can pull up this table. But I'm going to go ahead and just kind of flick to a new slide and pull up that table, and we'll just discuss some of those elements. Now, this is a screenshot I actually pulled out of our textbook, so I'd really recommend you get the ebook. And this is actually a screenshot, I think, from, I don't know if it's my phone or my iPad, but if you view it on a web browser, in a regular computer, maybe it'll look a little bit different. But this is it on my iPad, and so there's a little hamburger menu at the top, and so you can go to each section. And so we're in section 1.4 right here, And notice it has these little hyperlinked things here, so in red, and there's a little boing boomerang kind of little table up there to one side. You click on that, it goes full screen, and then underneath, this is your table itself here. I was making some instructions for someone. This was step number 5 to how to see the table, so that's where the 5 is coming from. So let me just kind of pull the table up by itself. So here's the table here. So these are the elements that I think you should know and have memorized. And there's sort of 2 columns to worry about. There's the element symbol, so Al here, and there's the element name, aluminum, over here. So you have to know these pairings. So flashcards work tremendously well. So take a flashcard, whether paper or electronic, right, and write the symbol on one side and the name on the other. And make sure you get the spelling of the name right. So some of these names are a little tricky to spell, so make sure you're happy with them. Again, argon, AR, first 2 letters, AR, just like aluminum. But we go down to some of them here. Let's see. Chlorine, so notice it's not CH, it's CL. So some of them are a little bit tricky. And let's go all the way to the right-hand side here. So there's the Latin names here. You don't have to learn the Latin names. I think the first year I ever taught this course, I said, make sure you memorize this table. And I had a whole bunch of people who regurgitated the Latin names on the exam, and bless their hearts, they'd learned cuprum and aurum and ferrum and argentum and so on. But you really don't need to know that unless you're a trivia nerd. So I would say it's enough to know copper is Cu. You don't really have to know cuprum, although later on we'll find that copper and iron are actually useful to know, whereas the other ones are really irrelevant. So have a look at this one here. So potassium, right, is K, is after calcium. So, and there's sodium, right? So that natrium right there. So tin, stannum, right? So you can see the element symbol, right, is related to the Latin name for a lot of them. And some of them, like the S for sulfur, right, it's pretty clear it's based on the English name.